Exam 1, essay question 1. Today we're going to address homeostasis, as well as protein-mediated diffusion and osmosis and what those things mean. Okay, so first off, we're going to start with homeostasis. Homeostasis is the body's ability to maintain a variable. So just use a quick example. We also use body temperature. And if we map our body temperature over time, we see that our body temperature goes up and down and up and down and up and down and up and down, ranging from anything from 96 to 99 or varying on the person. But what happens in this is we get this range of what is expected to see in any individual, or specific to each individual. What happens is the body is trying to maintain a certain set point. So most people think it's about 98.6, and it varies a little bit. Typically it's a little lower, but just to use it for an example, 98.6 is the set point. So as we get too warm, our body naturally cools us down. As we get too hot, our body naturally warms us up. And so this is the idea of homeostasis and how it works. The way it works is it uses what's called the reflex control pathway. So the reflex control pathway is pretty simple. It starts with a stimulus, which a receptor senses, which sends a signal through an afferent pathway to a control center. Lots of times in the body, the control center is the brain, but depending on the system, the control center can change. For example, with insulin, the control center might be the pancreas. So from the control center through an efferent pathway, it signals an effector to either be released or to change something, right? That effector goes back and affects the stimulus, therefore repeating the cycle, right? So let's start, and it's trying to return to the set point, sorry. So let's use our example of body temperature, right? So let's say we're too hot. So our stimuluses were too hot. So what happens is our skin or whatever will be our receptor. Our dermatomes are going to sense that we're too warm. So it's going to send a signal to our brain, right? That's our control center. It's going to say, hey, we're too hot. It will then use those efferent pathways to communicate with the sweat glands. And in most examples, there's many effectors, right? When we're hot, we sweat. When we're cold, we shiver or whatever. And there can also be other factors besides the most common ones. You know, it can increase blood pressure. It can dilate or constrict peripheral resistance, our veins, so then it pulls our blood inward or pushes it outward depending on if it needs to cool, right? So if we're too hot, it might dilate some of the veins that are in the some of the arteries and veins towards the exterior of your body, so the blood rushes to the skin and gets cooled. But in this example, we'll just use your sweat glands. Sweat, so right, it's going to cause the effector to sweat. When we sweat, we decrease in temperature. So we go back, decrease temp. So now we're at the right temperature. And that's kind of what this cycle is, right? We get too hot, we set, we go back down to the set point. We get too cold, we shiver, we get back up to the set point, etc. This is referred to as a negative feedback system, or negative feedback loop. And the reason it's called negative feedback is because it causes the opposite of the stimulus, right? So in this example, too hot. Sweat causes us to cool down. So it's the opposite of the stimulus. And this is very important. Most systems in our bodies work this way. Blood pressure does, temperature does, regulating blood sugar does, all based off of negative feedback. However, there are some examples of positive feedback. We're going to talk about two types of positive feedback, intentional and unintentional. Positive feedback, some examples of intentional. Intentional positive feedback can be giving birth, blood clotting, and action potentials. So let's just go through the reflex control pathway again for giving birth and blood clotting, right? So as you give birth, or as a woman gives birth, as she starts to have contractions, what happens is the cervix starts to stretch. Cervix stretches, right? So those contractions or the cervix stretching, this is your stimulus. So then as the cervix stretches, it sends sensory neurons, right, up to the brain. And these efferent pathways don't always have to be neurons. It can also be through bloodstreams to get it to whatever the control center is. So the receptor might be neurons in this example, and then our control center will once again be the brain. So your brain recognizes that the cervix is stretching, but the woman doesn't want to have the opposite effect, right? She doesn't want to have her cervix tighten and not stretch, or else birth would be impossible. So the brain sends a signal through efferent pathways to the effector, which in this case could be oxytocin. Oh, I spelled that wrong. Oxytocin. So in this case, oxytocin is a hormone that causes the woman to contract. It increases contractions, which leads to the cervix stretching more, right? So we have the same pathway involving a stimulus, involving a receptor, control center, effectors, the afferent and efferent pathways, right? It goes back, but instead of returning to normal, if we have cervix size over time, typically, just like in negative feedback, it would follow a pattern. However, with positive feedback, as it stretches, right, we're at a normal level, it stretches, the brain senses it, right, it's going to cause it to increase. So this normal set point, it's moving away. There's a bigger gap. So that's the difference between positive and negative feedback. Negative feedback returns to the set point. Positive feedback pushes it away from the set point. So just to give another example, with blood clotting, right? When your body senses blood clotting, it wants to keep blood clotting, right? That way, if you have a big cut or a gash or whatever, your body clots it all and you don't bleed out. So you sense that there's a cut, there's a gash or whatever, some kind of perforation. Your brain recognizes it, or whatever the control center would be, through receptors in the skin, right? You're bleeding. It sends coagulant. It goes back, starts clotting, and when your body recognizes it's clotting, it creates the same thing. Releases more and more coagulant so that your blood clots more and more and more at that one spot until you've reached a point where there's a blood clot there, right? You have a scab. So these are all intentional. Your body wants to do these on purpose. It helps keep you alive. But sometimes there's unintentional positive feedback. So to explain unintentional positive feedback, I just want to go over another negative feedback first and then talk about how it becomes unintentional positive. So we have blood pressure. which is very important. We want to maintain the right amount of blood pressure. But we have lots of factors of blood pressure. For example, we have blood volume, we have peripheral resistance, which is basically the size of your veins and arteries, and then we have heart rate. So those all affect blood pressure. So in a normal system, we have our typical range for blood pressure. We have our set point, whatever that is, over time. And so as we start to increase in blood pressure, for example, let's say we're exercising, right? So naturally our heart rate's going to increase. That causes our blood pressure to increase, right? Peripheral resistance might decrease, so then blood pressure goes back down. And it continues on, right? But let's say, for example, somebody gets cut. It's a pretty big wound. Their blood volume decreases. So naturally what would happen, right, as your blood volume decreases, your blood pressure is going to go down. So your body naturally is going to increase in heart rate and increase peripheral resistance so that it comes back up to a normal level. But what happens sometimes is if this cut is so big, right, you're bleeding out a lot, eventually your blood pumps really fast, your heart rate's increasing, so that it pumps out more and more and more blood, right? More and more and more blood. Eventually the person doesn't have enough blood to keep their heart busy, so their heart rate starts to decrease. And when their heart rate starts to decrease, right, blood pressure can't be maintained. So then it decreases, and it decreases, right? And so your heart's trying to compensate, trying to increase speed, keeps pumping out blood, you keep losing blood volume, your peripheral resistance is trying to compensate for it, but it's not enough. Or we could even say that your peripheral resistance is broken. It's trying to move the wrong direction too. That creates positive feedback. So that is what happens when it continually moves away from the set point. So it might look the same on the graph, right? Continually moves away from the set point. However, unintentional feedback is almost always bad. It is a reason we have interventional medicine, is to help prevent things like this. So just to mention, there is another type of negative feedback called insufficient negative feedback. And it's different from positive feedback because the body's doing something, it's fixing something. So let's use blood sugar as an example. To talk about the reflex control pathway, increase in sugar in the blood, sensed by the pancreas. The pancreas reacts, releases insulin. Insulin is the effector. It's going to decrease the amount of sugar in the blood, right? So we have our natural set point, or our natural range. We have our set point. Our blood sugar increases. Well, now our body tries to lower it by adding some insulin. Now, if instead of going immediately back down as it normally does, if it starts to go down, but then isn't enough, and it continues to go up, this part of the graph is known as insufficient or insufficient negative feedback. The body's trying to compensate, nothing's broken yet, but it doesn't work. Then we would enter positive feedback up here as it moves away and the insulin is no longer working, right? Something has to be broken here to have unintentional feedback, right? The heart rate breaks when it decreases because there's not enough blood, and the peripheral resistance breaks when it dilates instead of constricting to try and maintain blood pressure. And that happens once again because of lack of blood, right? Not enough blood, the heart can't pump enough, so the veins and arteries aren't getting enough blood, so they dilate to try and open up more space for the blood, causing it to decrease, causing positive feedback. So that should give you enough examples of positive and negative feedback. We're going to move on to protein-mediated transport. So before we talk about protein-mediated transport, I just want to touch on really quick simple diffusion. So if we have a membrane, if we remember from Bio 180, here we have our phospholipid bilayer. The outside is hydrophilic. The outside's hydrophilic, the inside is hydrophobic, which means the inside doesn't like water, but the outside does. So some small nonpolar molecules can naturally move through the membrane, as well as some molecules are also hydrophobic that like being in this environment. They can pass through the membrane through simple diffusion. To define diffusion, diffusion is how solutes move to match, to find equilibrium. So for example, solids might be in different gradients. So if there's more gradients or more solids inside the cell than outside, naturally these are going to have a concentration gradient force upon them to try and pull them outside the cell to make it equal. So this is simple diffusion. There are lots, so you could say it's non-specific in the sense that there are lots of different types of molecules that can pass through, whether it's CO2 or oxygen or a sterol, and it just naturally will pass through to create equilibrium. And the rate at which it happens is based on the concentration gradient. The bigger the gradient, the faster it's going to move because the greater the force. However, no energy is required, right? You're not using ATP for this. There's not a lot of competition, but it can move either in or out of the cell, depending on the concentration gradient. Sorry. So let's move on to other types. So the first type, we have facilitated diffusion. This is also another form of passive diffusion in which no energy is used. So the cell uses natural things to cause these concentration gradients to occur, and they use protein channels. Protein channels are very specific. Each channel typically only allows one type of ion and either the hydrated or non-hydrated version of that ion to pass through. But these channels use many different means to regulate what comes in and out. And we typically call these gated. There are multiple types of gated. There's ligand gated. So that means, for example, if we have a gate that closes here, it has a receptor and a specific type of ligand or protein, a certain molecule can come in and bind here, cause the door to open. So if that occurs, then we get an open door, right? Stuff can go in and out now when the ligand is binded. We also have voltage mediated gates. So the charge of the cell in and outside of the cell, typically the inside is negative and the outside is positive. And so it might have a certain plug in here, we'd say, kind of a thing. And it's attracted to positive charge. For example, it's attracted to a certain voltage, but to be non-specific, let's say it's attracted to a positive charge. When the cell is more negative and the outside is more positive, it's going to close. It's going to come in and come towards the positive and clog this channel. However, when the cells are more equal or negative, it'll float out and allow the right ions to flow through. We also have mechanical gates. Mechanical gates open for touch, temperature, pressure, these kinds of forces to regulate what comes in and out. And the last kind is called a leakage or leak channel. And what happens with a leak channel is it opens and closes itself, open, close, switching between the two to allow things to come intrinsically into the cell. And this is mostly based off of, once again, the gradient, right? As the gradient, electrochemical gradient increases, it opens. As it decreases, it closes. And so I just want to take a second to talk about rate, right? We talked about how this has no energy. It's very specific, but there are a couple of factors that deal with this. And we can use an equation. It's called the rate of diffusion equation. It's written as J equals negative dA times delta C over delta X. So what this equation means is J is the rate of change, so it's a way to, or rate of diffusion, rate of diffusion. So this is a way to calculate the rate of diffusion. D is known as the diffusion coefficient. So the diffusion coefficient is based off of the size and solubility of a particle. If a particle is smaller, it's going to diffuse easier. If a particle is larger, it's going to diffuse slower. Same thing with solubility. If something's really soluble, it's obviously going to diffuse better than if it's non-soluble. A stands for the surface area of the membrane in between the two surfaces, right? The thicker the membrane, the slower it's going to be able to pass through. Then we have delta C, and this is the concentration, the change in concentration between the two sides, right? The concentration gradient. What is the difference? Is which side has more, how much is it more, right? Bigger gradient, gonna move faster. Smaller gradient, gonna move slower. And then this X stands for the thickness of the membrane. I made a mistake earlier. In terms of surface area, if the surface area is larger, there's more room for things to move through, so it's going to move faster. If the surface area is smaller, it's going to move through slower. And then in terms of thickness, the thickness is how thick the membrane is. The thicker the membrane, the slower it moves. And I bring this up because it applies to the diffusion, both simple diffusion, facilitated diffusion, and as we continue, the other two types of protein-mediated diffusion, carrier-mediated diffusion, and active transport, but it also applies to osmosis, which we'll get to a little later. Kind of the same principle when we're talking about rate, but this is the equation we're going to use based off of Fick's law, and that's important to be able to calculate the rate. Once again, facilitated diffusion relatively is typically quick, versus what we're going to talk about next, which is the last type of facilitated diffusion that doesn't require energy. This is called carrier-mediated diffusion. So in this instance, instead of having a protein channel in the membrane, it has a carrier protein. So we'll just draw it like this, right? This carrier protein accepts, we'll say, little circles. Here are the receptors. So as these circles float about, they'll bind into these pockets. And when all are bound, right? We have all of them bound. It's going to cause a conformational shift in the protein, and then the protein will open to the inside, releasing these to move inside. Typically, these are intrinsic, but this is the process. Then once these molecules are released, whatever they are, right, it's specific for each carrier protein, it will conformational shift back to the beginning, and it will repeat this process. This, once again, doesn't require energy. It is using the concentration gradient. So the concentration outside is high, the concentration inside is low. So the molecule naturally wants to move from high to low. You can do the same thing with facilitated diffusion through protein channels. Outside is high, inside is low. And with these, sometimes it can also apply the opposite way. The inside is high, the outside is low, and so it moves extrinsically. And the same thing with simple diffusion, moves high to low. These are all facilitated simple. They all don't require energy, so it's always moving high to low. That's very important. But this, with carrier-mediated protein, we see something else that can cause problems. Two things actually: competition and saturation. So competition is, let's say we have some yellow half circles. another type of protein or molecule that looks similar in shape to these circles. However, it's not the same, right? Well, it might have enough similar features to the red circle that it can put itself in inside the receptor. And what happens is this yellow half circle, whatever molecule it is, it doesn't cause a conformational shift, so it stops this thing from happening. So competition from other cells or from other molecules is when something is similar enough that it can bind to the receptor or block the receptor and cause the conformational shift to slow or stop completely. This means that this carrier-mediated protein, this carrier-mediated diffusion is going to stop, at least with this protein. And it'll get moved and eventually start working again, but it can slow the rate significantly. The other one is saturation. If all of the same carrier-mediated proteins are going as fast as they can, right? Because it takes time for it to shift and change and release and then shift back, right? If there's such a big concentration gradient outside, as it moves them inside, what's going to happen is it reaches a point of saturation, which is where it's moving at its maximum rate. And this maximum rate can be whatever, but when it reaches that maximum rate, it's not going to be able to go any faster to compensate with a higher concentration gradient. It stops at that maximum speed and maintains it. So now just to talk about active transport, all the ones we just looked at were all passive. They require no energy. Active transport, it moves concentrations from low to high. So it moves against a concentration gradient. So if we have a cell here, let's say we have a sodium-potassium pump. It kind of looks like a carrier-mediated protein in the sense that it attaches to one and then conformational shifts and releases into the cell. And so what happens here is ATP comes in, ADP plus an inorganic phosphate comes out, but two potassiums will bind, it will shift, releasing them inside. Three sodiums will bind and come out of the cell. So that means the sodium in the inside has a low concentration, but outside has a high concentration, and it's pushing out the sodium. It does this to do what is called secondary active diffusion. This is called primary active diffusion. We'll talk about that next, how it uses sodium. And then it brings all these potassiums inside the cell because it wants to have a high concentration of sodium or potassium, and there is a low concentration outside. This is called primary active. Primary active transport always uses ATP. Always, that's very important. Both types of active transport require a certain source of energy. The source of energy here is ATP. Can have similar problems as carrier-mediated. It could have competition, it could have saturation. And in this example, one is moving out of the cell, one is moving into the cell. So now let's move on to secondary. Secondary active transport happens when the body doesn't, or the cell doesn't use ATP, but instead it uses an electrical chemical gradient, right? So we just talked about before how there's lots of sodiums outside the cell. So our body uses it to its advantage, right? It's high here, it's low here. It uses it to our advantage to pull in the sodiums and then move something using that energy to move it from low to high. Let's just assume the outside is low the outside is high and the inside is low. So I can't name a specific molecule, but for this example, we'll just talk about calcium, right? So we'll say calcium is, this is backwards again. It's low outside the cell and high inside the cell. I don't know if that's actually true, but so your body naturally wants it to come in. So your body will accept a couple sodiums, and then it will accept a couple potassiums, and the sodium naturally wants to come inside, so cause that conformational shift, like we're talking about. The calciums will be released inside, and so the sodiums. But the difference is this is moving low to high. This is active transport. It uses the electrical chemical gradient because it's negative inside the cell, positive outside, so the positive attracted to the negative, as well as the high to low concentration gradient to pull the sodium inside, pulling with it the calcium using this protein. So this is referred to as a symporter. We have two types. A symporter means the one that is moving high to low and the one that's moving low to high, they're moving in the same direction. They're both moving in. We also have an antiporter. An antiporter is when one is moving in and one is moving out. A good example of that is this active transport here with sodium potassium. All right, sodium is moving out of the cell, potassium is moving into the cell. Therefore, we could consider it an antiporter. I believe that kind of covers everything when it comes to protein-mediated transport, both for primary and secondary, as well as it covers the topics of specificity, right? All of active and facilitated are all very specific. They only require or allow one ion, whether it's hydrated or not hydrated. They have just one selected, so they'll have just the hydrated version or just the unhydrated version going through that specific protein. There's competition. They can reach a level of saturation, which is the max rate, and they always follow a specific direction, right? Active goes low to high, and a passive goes high to low. So to finish, real quick, we're going to talk about osmolarity. So osmolarity is the movement of water as it follows solutes. We'll get into some examples, but that's just the very basic definition. But we know if we have a tube and we put a membrane, that's another important part of osmolarity, the movement of water through membrane. As it follows solutes. So for example, if we have equal amounts of water on either side of this membrane, it's in equilibrium. But if we add salt, for example, to one side, there's more solutes over here than over here. And to try and balance that, water will flow through the membrane and increase the water amount. So the water here will go down, the water here will go up until it reaches an equilibrium. And so in terms of osmolarity, we use several topics to talk about it. The main one being osmolarity. Osmolarity is the way we measure how many particles are in a certain solution. This is just a little different than molarity, which is the number of molecules. And that sounds very similar. But if we take again our salt example, NaCl, and we have a 1.0 molar solution, right? That means we have 1 mole per liter of sodium chloride. These are both per liter. What happens with osmolarity? Osmolarity recognizes that sodium chloride dissociates at a constant of 1.8. So it multiplies the I constant, the dissociation constant, with the molarity to become 1.8 molar, osmolar, 1.8 osmolar. So in this situation, it accounts for the dissociation of certain products, which is very important because the number of particles is what the water is going to follow, right? So we'll give some examples of that in a minute. But one more word we want to talk about is tonicity. Tonicity is the toneness of a cell and what happens in the presence of two solutions. And so tonicity can also apply to other things besides cells, right? It can apply to any system, but it refers to the interaction and what happens, where the water goes, and how it changes the shape of the system or the cell, whichever you're looking at. And so we use a couple of Latin prefixes to explain these relationships using osmolarity and tonicity. Hypo means less, hyper means more, and iso means the same. So for example, if we have osmolarity, we have something that's hypoosmolar. I think that's the name. Hypoosmolar. What's going to happen? That means it's less osmolar, right? So in this case up here, if we look at this as solution 1 and solution 2, solution 1 is hypoosmolar, has less particles. But then if we look at solution 2, it is hyperosmolar. Hyperosmolar because it contains more particles. And then isoosmolar is when it contains the same amount. And if we apply the same thing to tonicity, we can look at how a cell is affected by the difference in osmolarity. So let's say we have a cell here, typical cell, and the human body has 300 milliosmolar of particles in it. So let's put it in 0.9% NaCl solution, also referred to as saline. This also naturally has 300 milliosmolar, or close to that, in the solution. So in this example, it's important to know the permeability of the solute because NaCl is non-permeable. It can't pass through the cell membrane. So what happens is we have 300 milliosmolar inside, we have 300 milliosmolar outside. So if we compare the two, right, we would consider them to be isoosmolar, having the same amount of solutes. And then if we compare the tonicity, water is not going to flow either direction, or there is going to be water flow, but there's going to be no net change of water flow. And that's really what's measuring, because there's always water passing through. It's just whether or not it is changing the net volume of the cell in solution. And so what happens is we could consider isotonic. The reason for that is because the cell shape doesn't change, right? The solution doesn't change. It's going to have the same amount of water in it. So we'll use another example. Let's say instead of salt this time, right, we add 5% dextrose. 5% dextrose also is 300 milliosmolar, right? So when we start, 1, 2, 3, 4, 5, we look at them and we say, oh, they're isoosmolar again. Isoosmolar. Sorry. They have the same amount of particles, the same amount of solute. But dextrose, unlike salt, is permeable. So that's why permeability is super important to osmosis, is because it can change the tonicity, right? Isoosmolar, but dextrose is going to pass through, right? There's a concentration gradient. There's more dextrose outside than inside. Moves in, the cell naturally is going to metabolize it, and it's all going to disappear. So now we're left with just what's inside the cell and nothing outside the cell. So that means there's a 0 milliosmolar outside the cell, which, as we talked about earlier, therefore makes it hypotonic, right? The solution has less than what's inside, therefore it's going to decrease in water to try and match the concentration of solutes on each side. The cell will then swell, and then it will burst eventually because of the tonicity. So in some cases, osmolarity and tonicity are the same, but in many cases, the osmolarity and hypertonicity, the osmolarity and tonicity can be different. And so we'll use 2 more examples, right? It's important to know if something is permeable as well as if it is metabolized by the cell. So once again, we're going to use the cell, we have our 5 dots. Now we're gonna have our dextrose, 1, 2, 3, 4, 5, our 5%, same thing. We're also gonna have our 0.9% saline. So now we have 10 particles, or 600 milliosmolar outside, and only 300 inside, right? That's going to make this hyperosmolar, right? The outside has more than inside the cell. What happens though, as we know, dextrose is going to move into the cell and get used up and metabolized, leaving us just with our saline. So now we have 300 milliosmolar inside and outside the cell. This makes it isotonic, meaning the cell isn't going to swell or shrink. Shrinking is also referred to as crenation. So we're going to use one more example. This time we're going to use well, we'll do 2 more examples. This time we'll use urea. We have our 5 dots, our 300 milliosmolar. We'll use urea, 300 milliosmolar, the urea. Urea is permeable, like dextrose. However, it's not metabolized by the cell. So we'll get some passing inside, right? That's going to lead us to a container with 450 milliosmolar inside the cell, 450 inside the cell, and then only 150 outside the cell. So because of this, right, in our original, they're isoosmotic. But what happens after it moves is there are less particles outside than inside, and so it becomes hypotonic and moves in. And in all these situations, we're using the solution as our frame of reference. If we change and we choose the frame of reference as the cell, in this example, we would say the cell is hypertonic to the solution. And because it's hypertonic to the solution, right, water's going to come in from the solution. We get the same result, but it just depends on the frame of reference. Typically, the frame of reference is always the solution. So to give one more example, instead of using 0.9%, if we use 1.8% sodium chloride, it has a natural osmolarity, it's going to have 600 millismolar. Since it has 600 millismolar, it's going to be greater than the cell. Oh, sorry, wrong color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so has a greater amount of solid outside the cell, so we would call this hyperosmotic. Right, but water is going to flow outside the cell because there's more solute per concentration outside the cell, because water accepts all molecules as the same, right? With osmolarity and with diffusion, it's specific to each solute. But with osmolarity and the movement of water, it attributes them to all be the same, right? So water's going to come out, this cell is going to crenate. Ooh, it's going to get smaller, it's going to shrink. That's what's going to happen, right? So we could say this is hypertonic. Just one more quick example. Sometimes the cell can also be hypoosmotic. So if we have 0.45% saline, we're gonna have less outside than inside, right? And so naturally, once again, it's going to be hypotonic. The water will flow inside the cell, cause it to expand. That should explain pretty well how tonicity and osmolarity are related but different, right? We can have a hypertonic and a hyperosmotic solution, but we can also have a hyperosmotic and isotonic solution. So it changes depending on the permeability, the solubility, as well as if the if the molecule can be absorbed and digested or metabolized by the cell. And this changes depending on the solute. So that wraps up everything on osmolarity, protein-mediated transport, as well as homeostasis. I sure hope you watch this video in 2 times speed. I'm sorry you have to watch so much.